Hi, everybody. Welcome to another Extreme Performance Series video blog edition. Today, I'd like to talk to you about Tanzu. And when we bring that topic up, I wanted to pull in a very strong peer of mine, Karthik, to share some of his real-world experience and expertise with you as well. So, Karthik, why don't you go ahead and give yourself an introduction?
Hey, hi, folks. I'm Karthik Ganesan. And Mark, thanks for having me over. So I have, a broad experience in cloud system performance with special interest in hardware acceleration, resource management, operating systems, and middleware. I've been with VMware for 4 years now, and I lead the application performance efforts for the Tanzu product portfolio.
Well, that's awesome. Well, let's take a look at what you have for us today.
Before I get to the content, I thought I'll give a quick refresher on the vSphere Tanzu architecture, so that it gives enough context for everybody to consume some of the things that I'm going to talk about. Right. So let's say you have a vSphere with an NSXT data center, right? And say you have a vSphere cluster on it, and since it's an NSXT data center, you have your NSX related appliances like your NSX Edge and your NSX Manager and stuff like that. Right. Go through workload management UI in the vCenter and convert this vSphere cluster into a Kubernetes cluster, or what we call a supervisor or a management cluster. Right. In a management or a supervisor cluster, basically your ESX hosts transform themselves into a Kubernetes node. Right. So let's say you have some workloads, some Kubernetes workloads that you want to deploy on your setup. And the first thing that you do is to create some supervisor namespaces. So what's a supervisor namespace? You can think of it as a resource pool, right? Like, so you get to have, a Kubernetes cluster where your Kubernetes nodes are your virtual machines, right? Like you could have, a bunch of those guest Kubernetes clusters deployed on top of this management cluster, right? And when you do that, you get to choose, hey, this is the number of control plane VMs I need, or this is the number of worker nodes I need in my Kubernetes cluster. So you get to carve out your infrastructure into these smaller Kubernetes. You also get to choose, like, hey, how big should each of these nodes be? And also you get to choose the class in which these workers or these control plane VMs belong to. Like you could say, hey, I need them guaranteed. I need to have reservations for CPU and memory for these underneath, or not. They'll just be, a best effort TKG node. So hopefully with this, background, now you can start deploying your workloads. Say I want to deploy one of my workloads as a native vSphere, workload. Right? Basically, each of those Kubernetes pods get deployed as a native pod on the supervisor namespace or on the management cluster directly. Right? Or you could take some of your workloads and then put them on inside these guest Kubernetes cluster or the TKG clusters, right? So now with this background, I also want to touch on the network architecture of a Tanzu setup, so that we can go ahead and talk about some things like the load balancer. Let's say you have a vSphere 7.0 setup, and say you have 3 ESX hosts in your vSphere cluster, right? And say you have enabled workload management, and say you created 2 namespaces here, namespace A and namespace B, and you have some vSphere pods in each of these namespaces, right? So what happens underneath the Tanzu machinery is that you automatically got a load balancer created on your NSX Edge, that is fronting pretty much all the Kubernetes services that you are going to create in this supervisor cluster or the management cluster. And then it's connected to a tier 1 gateway, that to a tier 0 gateway, and that then it goes to the outside world. Now, let's say you deploy a TKG cluster, into one of the namespace here, right? So what happens when you do that is you automatically get another load balancer spun up for you, and a tier 1 gateway created for you that connects to the outside world through this tier 0 gateway, right? So this is in, typically if you take a 7.0 GA build and you bring up a setup like this is how it's going to look underneath the covers, right? But there have been some changes that have been done in 7.0 P02 or the patch 2 and later. So let's say the exact same setup, but if you had this deployed on a 7.0 P02 or a setup or a version later than that, basically up to this, it all looks the same, right? Like I have 2 namespaces, one, namespace A with some vSphere pod, namespace B with some vSphere pods, and in namespace C, I have, a TKG cluster, right? The difference here is instead of one load balancer for the entire supervisor cluster, these what you get now is every time you create a namespace, in the supervisor cluster, you're automatically going to get a load balancer deployed for you, right? So this gives you more control over your workloads, and if they are load balancer intensive, you get to carve them out in different ways that will be most useful for the application performance and things like that.
So good background there, Karthik, and I think that's kind of an important point here. So what you're explaining is the fact that moving to 7.0 patch 2 or later, we've changed the number of load balancers that get spun up, and it's really based off kind of that namespace segment. So the net result here is you're telling me that that's been a bottleneck in the past, correct? That would be a common one that our customers would experience.
Yeah, exactly, right? Like, if say you had some Kubernetes services that had very short connections, right? Your load balancer can run out of juice very quickly, right? So now this gives you a lot more control over, your infrastructure, and you get to scale better, even if you have something that is load balancer intensive.
So I know you're a man of science, so I have to expect here you have some data you can show us that'll kind of show how much of an increase we got out of this change.
So in this case, you can look at this chart here on the left. So I have my y-axis is the throughput, or the number of concurrent users that this setup is going to be able to handle, right? And I'm using this application called Weathervane 2.0. So basically, the higher, the better in terms of this y-axis. So this is the application throughput right here on y-axis. In terms of x-axis, the first setup I have here is one large TKG cluster, and has 12 worker nodes. So when I have that, I'm able to support up to 31,800 concurrent users without failing my quality of service, right? How do I know whether I am running into the limits of my load balancer, right? So in this case, this whole TKG cluster lives inside one supervisor namespace, and therefore, all the Kubernetes services on this is going to share this one single name load balancer, right? So the best way to go about finding if my load balancer is becoming a problem or it's becoming a bottleneck is to go and look for alarms on the NSX unified uplines or the NSX manager, right? So typically, if you had a load balancer problem, this is what you will see in your alarm screen. You could go in, and if you click through this, you might even see errors like this. The load balancer virtual server blah blah went down, and then it came back up kind of messages. This load balancer was overwhelmed at some point of time, and some of these virtual servers that are fronting your Kubernetes services went down, and then later on it was resolved and it was brought back up, right? So this is a very telltale sign that hey, this one single load balancer is being bottlenecked in this case, and I got to do something about it. So what do you do about it if you have a situation like this, right? If you are with, let's say, a 7.0 GA, something before the 7.0 P02, what you do is you go ahead and break this large TKG cluster, and you make smaller TKG clusters so that each one of them can get their own load balancer, and you go ahead and segregate your Kubernetes workloads, put some services on each of these different clusters so that each of them they can have their own load balancer, right? But if the same is a 7.0 P02 or a later version, what you do is you do the exact same thing. You break this large cluster into smaller clusters, but you also put them into different namespaces, because after 7.0 P02, every time you create a namespace, you are getting your own load balancer, right? So now the same workload that I had, now instead of having one large 12 worker cluster, I'm creating 6 small 2 worker clusters, and each one of them is getting their own load balancer. And now what happens is my performance goes up. Now I'm able to support up to 45,000 concurrent users, right? So basically, in this data point, the load balancer was the primary bottleneck, right? I was limited by the load balancer. But now after this change, after breaking them into smaller clusters, the load balancer is not the bottleneck anymore. The bottleneck has shifted to something else, right? So now this is all about the TKG clusters, right? I just talked about this whole thing in the context of TKG clusters, but honestly, the change in 7.0 P02 is even more relevant to the native pods or the supervisor cluster workloads. Right? Basically, previously, all you had was one load balancer for everything that was deployed in your supervisor cluster. But now, if the same workload, if I just created 6 different namespaces and put my the main pods into each of these 6 namespaces, I would have got a similar performance bump with this on the supervisor cluster. Now you have more ability to scale and use your infrastructure all the way by also being able to scale your load balancers by creating new namespaces.
Well, and I think that's an interesting point that you highlight there. The fact is, the infrastructure didn't change under here. We're just able to utilize it better, right? Because now we're not bottlenecked on that load balancer. So that idea of scale and use of that infrastructure is kind of really important. So excellent data point to kind of show how those changes will support scale better for those type of workloads. Mm-hmm. So another question for you then too is, okay, along those same lines, we talk about virtualization being necessary for this type of workload class because we want to consume all of those hardware assets we have. Understand you have some data points you can show us around that too.
Sure. So let's get to another experiment that I want to talk about, right? So I'm going to talk about how you can consolidate using the best effort TKG nodes in this particular slide, right? So if you chose the guaranteed class, basically what you get is you get CPU and memory reservations underneath for those worker VMs or your control plane VMs. Right? But they're the same, with the best effort class, you don't have those reservations underneath, right? So let's say, for my experiment, I had a host with 32 physical cores, and I am deploying 4 extra large workers in each TKG cluster. I consume about 16 CPUs. Right? So now you can do your math with a host with 32 CPUs, and I'm gonna keep deploying my TKG clusters into the same host. I'm gonna, I can fit 2 of these without overcommitting, right? Like 2 16 CPU TKG clusters into it without overcommitting, right? So, and I'm gonna run the weather vane application that I talked about before inside each of these TKG clusters so that it can, give us this aggregate performance to look at, right? So initially I have just one TKG cluster, and and these are independent experiments. This dark blue and the other point here, they are independent experiments. Right? In one experiment, I'm using the best effort TKG worker nodes, and in the other one, I'm using guaranteed TKG worker nodes. Right. So initially, I'm having only one TKG cluster. Than the the guaranteed performs slightly better than the best effort. Obviously, they have some reservations underneath. It makes sense. So then what I do is I'm adding 2 such TKG clusters. So this data point corresponds to 2 guaranteed TKG clusters running here. In this case, it corresponds to 2 best effort TKG clusters running underneath. And at this point, I'm at 100% usage of the CPUs. In terms of overcommit, I'm not overcommitting. Like 100%, I'm not meaning 100% utilization, but I'm talking about using all the CPUs in my VMs, right? If you look at the performance, from 1x to 2x overcommit, my performance still going up quite significantly, actually. So there is still a lot of juice on this host, even though I've actually used all of it up in terms of the guaranteed. If you think about it, I've allocated the 32 CPUs, but I cannot go any further in terms of guarantee, right? So, and then later you see performance goes down because at this point of time I'm overcommitting too much on this particular host, and then it goes down and then tapers off. So bottom line is a lot of their end users over provision their Kubernetes requests, right? Like end users, the DevOps users, they are not very sure what each of their microservices or their services actually need, and when they start overcommitting their Kubernetes requests, these requests can really add up. And what happens is they end up with very low utilization on their Kubernetes nodes, and the Kubernetes scheduler would not let them schedule any more parts because those requests have already added up to the node resource that they have, right? But with these best effort TKG nodes, what you get is you get to work around a problem like that, and you actually get to overcome it even with those Kubernetes requests.
And I think that's just a strong data point here. Again, too, that idea of as we look at, Kubernetes and clusters and how we scale all this stuff, I think a lot of people still don't understand the virtualization value. And right through the 2 data points here, you really showed the fact that, we can help scale by using multi-instance load balancers. We can help scale through this idea of overcommit, right? So there's a real strong value proposition here to use the VMware technologies to support all this and still get excellent performance, if not better performance than you could.
Very well said, Mark. Yeah. So to recap, respect load balancer limits. Keep an eye on your NSX manager, and if you want to consolidate and overcome it, go use the best effort TKG nodes, and you can still safely overcome it as long as you keep an eye on those metrics like ready time and balloon and things like that.
Awesome. Well, Karthik, thank you for joining us today. Excited to have you back to share more with us about Tanzu and all of its various components.
Thanks, and please check out the links below this video with more details on the best practices.